Hello guys, thank you for watching this video lecture. I am Jalil Piran and I'm working as an associate professor in the field of artificial intelligence. Today, we want to learn about statistics. So the topics are the basics of statistics, population, samples, process, graphical methods in descriptive statistics, measure of location, and measure of variability. So let's dive in. Let's start with some basics. Data. Data refers to raw facts, figures, or information that we have collected through observations, measurements, or research. Data can be quantitative, it means numerical, or data can be qualitative, it means categorical. Data serve as the foundation for analysis and decision making in various fields like business, healthcare, technology, etc. On the other side, statistics is a branch of mathematics and the focus is on collecting, analyzing, interpreting, presenting, and organizing data. Statistics helps draw conclusions from data by identifying patterns, making predictions, and determining relationships. Statistics is crucial for making informed decisions, and it is used in various disciplines including economics, engineering, social sciences, and healthcare. Now, let's check some basic definition in statistics. Engineers and scientists are constantly exposed to collection of facts, or we can say data, both in their professional capacities and in everyday activities. The discipline of statistics provides methods for organizing and summarizing data and also for drawing conclusions based on information contained in the data. It means we can extract information from the data. An investigation will typically focus on well-defined collection of objects constituting a population of interest. So we can say that statistics is the discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. An investigation will typically focus on well-defined collection of objects that we say it's a population of interest. For example, in one study, the population might consist of all gelatin capsules of a particular type produced during a specific period. When desired information is available for all objects in the population, then we have what is called as census. Constraint on time, money, and on other scarce resources usually make a census impractical or infeasible. We cannot go for collect data everywhere. For example, if we want to predict the percentage rate of attending an election, it is impossible to go and ask everyone one by one. Instead, a subset of population, we call it as sample. So, a subset of population is selected in some prescribed manner. Later, we will talk more in details. So, type of data. Data can be classified in two main categories. One is qualitative or categorical data, and the other one is quantitative or numerical data. So in the case of qualitative data or categorical data, this kind of data describes characteristics, labels, or attributes, and we cannot measure them numerically. For example, nominal data. These are categories with no inherent order. For example, gender, male or female, hair color, blonde, brown, white, ethnicity, Hispanic, Asian, black, white, something like that. Then In the qualitative data, we have ordinal data. These are categories with meaningful order or ranking, but differences between them are not uniform. For example, rank, first, second, third, something like that. Letter grades, A, B, C, economic status, low, medium, high, something like that. Then the second category of data is quantitative or numerical data. This type of data represent measurable quantities with numerical values. And we have two types, discrete data and continuous data. In the case of discrete data, it means they are countable values with no intermediate values. For example, when we say how many students, we can say two students or three students. We cannot say two and a half students, right? So the number of students in a class, the number of workers in a company, these are discrete. However, for the case of continuous data, they are measurable values that can take any number within a range. For example, height of children. For example, from 150 centimeter to 160 centimeter, how many possible heights are there? Infinity. Or the speed of car, infinity, right? So they are quantitative and continuous data. With the rise of digital transformation, vast amount of data are being generated every day. To extract meaningful insight from this data, disciplines like data science and machine learning have been emerged. Data science normally focuses on handling and analyzing large data sets, while machine learning, or ML in short, enables systems to learn patterns and make predictions without explicit programming. So, as the definition, data science is an interdisciplinary science about processing large amount of data using statistical models to extract insight from data, right? So, this field combines statistics, programming, and domain knowledge in order to analyze and process large data sets, like, for example, data cleaning, visualization, predictive modeling, in order to uncover valuable insights. On the other side, we have machine learning. Machine learning is a subset of artificial intelligence, and it involves with algorithms and statistical models. They enable computers or any device that has computational capacity in order to learn patterns from data and improve performance over time. So the word learning comes from improvement. Once they produce some response, next time they try to improve their response. It means they try to increase the accuracy of their response. Machine learning is widely used for tasks like classification, regression, clustering, recommendation systems, and many other tasks. So, in fact, machine learning is data plus model plus optimization. So data, we can define data as raw facts without context. For example, we say temperature today is 17 degrees Celsius, right? Then from data, we can go for information. Information we can define as structured data that provides some context. For example, weather reports specifying location, time, condition, etc. Then from information, we try to extract knowledge. We can say that knowledge is actionable information. So we can say knowledge is actionable information and it is used for decision making. For example, we know it's a cold day today and we decide to wear a light jacket. Then from knowledge, we can go for insights. Insight, it means recognizing patterns in knowledge over time. For example, we notice a trend of cool summer in some cities, right, in our location. So this is the insight. Then we can go for wisdom. Wisdom is understanding large scale systems and making long term predictions. For example, identifying climate patterns and using those patterns for future forecasting. And finally, we come to impact. Impact, in fact, goes beyond wisdom by driving meaningful actions and influencing real world outcomes. This impact involves applying wisdom to create tangible changes in behavior, policy, and systems. So, as I said, machine learning is only one branch of AI. So, in AI, we have four categories. The first one is problem solving by search. Here, we have different kind of search algorithms like uninformed search, informed search, constraint satisfaction search, adversarial search, and many others. Then we have knowledge, reasoning, and planning. Then we have learning, and the last is communication, perceiving, and acting. So in here we have like natural language processing, perception, pattern recognition, robotics. So out of learning here, we have machine learning, and in machine learning, we have four categories: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. And deep learning is somehow originally from supervised learning, but it can be used with others as well. For example, we have deep reinforcement learning, right? So in machine learning, we have several algorithms, and in deep learning also we have feed-forward neural network, UPNs, convolutional neural network, recurrent neural network, recursive neural networks, transformers, and many other algorithms. So this diagram outlines a typical workflow in machine learning projects. We break it down into several key steps. The first one is object definition. Object definition is the initial phase where the goal of machine learning project is defined. So it involves understanding the problem, defining success criteria, and determining what kind of prediction or classification are needed. Then we come to the data collection. In this step, relevant data is gathered from various sources. The quality and quantity of data are crucial for the success of the model. And probability and statistics play a role here in understanding data distributions, sampling methods, and ensuring that the data collected is representative of the problem domain. Then we come to the data preparation. This involves cleaning and preprocessing the data to make it suitable for modeling. Tasks including handling missing values, normalizing data, and feature engineering. Also, in this step, statistical methods are often used to identify outliers, understand relationships between variables, and transform data into a usable format. Then we can go for algorithm selection. Choosing the right machine learning algorithm based on the problem type like classification, regression, clustering, or others, and the nature of data is very important. Probability and statistics are fundamental in understanding the assumptions of different algorithms, such as Bayesian method, decision tree, or neural networks. Then we go for model training. The selected algorithm is trained on a prepared data. This involves adjusting model parameters to minimize error or maximize accuracy. In here, statistical models are used to evaluate model performance, understand overfitting, and ensure that the model generalizes well to unseen data. Then we can go for testing the model, prediction, can deploy the system. So you can see in most steps, statistical methods are very helpful. Some people, they think that, machine learning is that much easy that by watching video lectures or short courses, they can become an expert in machine learning. However, machine learning has some prerequisites. So these are the core areas of mathematics that form the backbone of machine learning. For example, calculus, this is essential for understanding optimization, gradients, and rate of change, which are critical in training machine learning models, like, for example, gradient descent. We have some other topics in here, like convergence and divergence, parameter optimization, parameter changes, and many others. Then statistics and probability, these are crucial for modeling uncertainty, making predictions, and evaluating model performance. They are used in probability distribution, hypothesis testing, and Bayesian models in machine learning. Then we have algebra family. Algebra family include linear algebra, which is vital for understanding vectors, matrices, and operations like matrix multiplication used in neural networks and dimensionality reduction like PCA. And also, it covers other algebraic structures relevant to machine learning. Real analysis and complex analysis, they provide a deep understanding of limits, continuity, and functions which are important for theoretical aspects of machine learning. Discrete mathematics is very important because it includes concepts like graph theory, combinatorics, and logic, and these are very useful in algorithm design, network analysis, and reasoning in machine learning systems. Basic and geometry are very important because they involve geometric concepts like vectors, distances, and shapes, and they are key in understanding data distributions, clustering, and high dimensional spaces. A loss function, Euclidean distance, we use them for optimization and evaluating model errors. Then we have information theory. Information theory focuses on quantifying information, entropy, and compression, which are fundamental in areas like data encoding, feature selection, and deep learning. Numerical computational and convex optimization is very important here. And we have some other prerequisite based on the requirement. So these are very important in order to understand. They somehow form the mindset of someone who is going to be an expert in machine learning. Statistics, particularly in the context of machine learning, is very important. Statistics help transform raw observation into understandable and shareable information using descriptive statistical models. They also enable reasoning from small samples of data to broader domains using inferential statistical models. So, statistics is a collection of tools developed over hundreds of years for summarizing data and quantifying properties of domain based on a sample of observation. Then on the other side, we have probability. Probability theory provides models of probability distribution to represent chance-based phenomena. A statistical model tests these models and rely on probability theory as their mathematical foundation. Probability is foundational for machine learning and essential for learners. Probability is a prerequisite in most applied machine learning courses and books. Probability methods are used at every stage of machine learning projects. Probabilistic frameworks support the training of many machine learning algorithms. So the key concepts depend on probability, including understanding data distribution and statistics, fitting models on training data sets, and interpreting stochastic learning algorithm performance. Machine learning learners need probability to be effective. But there is one question. What is the difference between probability and statistics? Probability and statistics are closely related, but they are fundamentally different in their approach. Probability starts with a known theoretical distribution and predicts specific values. However, statistics begins with observed data and work backward to infer the overall distribution. So if we say statistics come from past to now and probability goes from now to the future. Probability is deductive. We know the whole and we drive specific cases. But statistics is inductive. We observe specific cases and infer about the whole. We can say that probability goes from whole to part, and statistics goes from part to whole. It means we have, for example, distribution of data, and we know the mu and the standard deviation, then we try to find out the probability. For example, we have a given bias of coin in case of discrete. What is the probability of getting heads? Or we can say, what is the probability of rain tomorrow given the 2 days weather condition? Okay, we are going to predict the future. However, in case of statistics, we use sample data to infer the characteristics of larger population that we have. For example, from sample survey, we want to estimate the average income of a city, okay? Or we want to, based on past temperature records, we want to determine climate trends. So probability and statistics complement each other, with probability being crucial for forecasting and modeling, while statistics is a key for analyzing real-world data. Okay, so let's go back to definitions. A variable is a symbol. Typically, letters like we can use X, Y, Z. For example, X as a brand of calculator owned by a student. Y, the number of visits to a particular website during a specific period of time. Or Z as braking distance of automobile under a specific condition. These variables represent an unknown or changeable value. We shall initially denote variables by lowercase letters from the end of alphabet like X, Y, Z, W, U, or anything. Data results from making observation either on a single variable or on the same time on two or more variables. So we have univariate data. A univariate data set consists of observation on a single variable. For example, we might determine the type of transmission of a car. For example, we say A automatic and M manual, right? And we do it on 10 cars we recently purchased. So we say manual, automatic, 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 manual, automatic, and so on. We have bivariate data when observations are made on each two variables. For example, our data set might consist of weight and height pair of each basketball player on a team. So first one is weight and second one is height. Then multivariate data arises when observations are made on more than one variable. So bivariate is a special case of multivariate. For example, a research physician might determine systolic blood pressure, diastolic blood pressure, and serum cholesterol level for each patient. So you can see the first one, second one, and third one. This is called that multivariate data. So statistics has two main branches, descriptive statistics and inferential statistics. An investigator who has collected data may wish simply to summarize and describe important features of data. This entails using methods from descriptive data. It means we have already the data. Some of these methods are graphical in nature. The construction of histogram, box plots, and scatter plots are primary examples. Other descriptive methods involve calculation of numerical summary measures such as mean, standard deviation, correlation coefficient. The widely availability of statistical computer software package has made this task much more easier, or we can use Python easily to calculate these things. The other side, we have inferential statistics. It is another branch of statistics and it involves making prediction. It means we don't have whole data set, right? So we want to make prediction based on samples. We want to make conclusions or generalization about a population based on sample data. It goes beyond descriptive statistics by using probability theory in order to infer properties of larger group from a smaller subset. Estimation, hypothesis testing, regression analysis, correlation analysis, ANOVA analysis of variance are these methods for inferential statistics. So throughout the semester, we will study all of them one by one. There are common graphical methods used in descriptive statistics in order to summarize and visualize data distributions. These tools help in understanding the shape, spread, and central tendency of the data, as well as identifying outliers in patterns. The first one is stem and leaf display. Second one, histogram, dot plot, box plot, and many others. Bar graphs, we have frequency table, circle graph, line graphs, box and whisker plot, and many others. So here is one example. The website www.charitynavigator.com gives information on roughly 6,000 charitable organizations, and there are many smaller charities that fly below the navigator's radar screen. Some charities operate very efficiently with fundraising and administrative expenses that are only a small percentage of total expenses, whereas others spend a high percentage of what they take in on such activities. So here is a data of fundraising expenses as a percentage of total expenditure for a random sample of 60 charities. Without any organization, it is difficult to get a sense of the data's most prominent features. Just by looking at these 60 data, we cannot understand anything, and you imagine millions of data. So we should go for graphical presentation. Here, we can see one of the descriptive statistical tool. It is named as stem and leaf display. This stem and leaf display is a kind of graphical method to organize and visualize numerical data. So it helps to understanding the distribution, shape, and patterns of a data set while retaining the original data values. According to our example, clearly, a substantial majority of the charities in the sample spend less than 20%. So, having obtained a sample from population, an investigator would frequently like to use sample information to draw some type of conclusion. For example, make an inference of some sort about the population. So let me explain in details what happened here. In this graph, each data point is split into two parts, the stem and the leaf. As you can see here, 83 is 88, 3 plus 10, right? So it means 8 multiplied 10 plus 3 is 83. So 8 is here as a stem and 3 as leaf, right? So the stem represent the leading digits of the data, while the leaf represent the trailing digits. The stem consists of the leading digits of each data point. It forms the vertical axis of the plot. And then we have leaf. The leaf represents trailing digits of each data point. It is placed next to the corresponding stem horizontally, as you can see here. The stem and leaf plot allows for visualization of distribution of data showing the frequency and range of values. It preserves the original data while providing a clear overview of patterns and outliers. Let me explain how it works. For example, we have 183 in our data set. So let's find it 83. 83 is here. That's why we have 18 here and 13 here. Then we have 148 here. Then you can see here 48. Then we have 34 or 35 because it's rounded, right? So let's find it. So we have on 34.7. So it's rounded here and it is 35 here. Then in the case of 20, we have 26 here. So you can see 1, 6, 20, and 6. Then we have 20, 20, 20 here, 120 here. We have another 20 we have here, 21. And we have 90 here. So 90 is rounded to 20. So you can see here we have 24. So from this graph, we can understand that the most of the distribution of data is in here, less than 20%, 20% or less. Very few is more than 20%. So you can see from data set, it's very difficult, but using this graph, it's very easy. Next one is histogram. Histogram is a graphical representation of the distribution of numerical data in descriptive statistics. We use histograms to summarize and visualize the frequency of data within specific intervals, or we call them as beans or class intervals. So you can see here, this is 1, this is 2, this is 3, this is 4, this is 5, 6. So you can see these are called as beans or class intervals. This bar represents the frequency. It means in this interval, we have 35 frequency. In this interval, you can see we have like 15 frequency. In this interval, we have 5 frequency. So each bar height corresponds to the number of data points with a particular range. This is the particular range or bin or interval that we say. Unlike bar charts, histograms are used for continuous data, not discrete data, and these intervals are adjacent. Histograms help in identifying patterns such as skewness, symmetry, and modality like unimodal or bimodal. So statistical methodology is now widely utilized across numerous disciplines like molecular biology for analyzing microarray data to study gene expression. It is used in ecology. In ecology, statistics quantitatively describing spatial distribution of individuals in animals and plant populations. In material engineering, it is used for investigating treatment, mitigate corrosion. In marketing, it is used for designing market surveys and developing strategies for new products marketing. In public healthcare, it is used for identifying disease sources and evaluating treatment methods. In civil engineering, it will be used for assessing structural stress effects and analyzing traffic flow impact on communities and many more. So we can say the scope of modern statistics is very wide. Statistical studies can be broadly classified in two categories. One is enumerative study and another one is analytic study. The distinction between these two types is crucial in research and decision making as they serve different purposes. Enumerative studies focus on analyzing existing population, while analytic studies aim to improve future outcome through process understanding and innovation. So, in enumerative study, this type has a clearly defined objective and focus is on well-defined, unchanging population. As defined already, the population is typically a finite set from which conclusions are drawn. Then, a sampling frame is a list of sample points, is either available or can be constructed. An example of enumerative study is designed experiment, where data is collected from an existing population. On the other side, we have analytic study. Unlike enumerative study, analytic study aims to draw conclusions about the process that may not yet exist. And the goal here is typically to improve future outcome rather than analyze a fixed population. Since the study focuses on potential improvement, it lacks a well-defined sampling frame. We don't have sampling frame here, and its impact is often localized and shorter. An example for analytic study is the production industry. In here, new products are developed as enhancement to the existing one. Statistics deals not only with the organization and analysis of data once it has been collected, but also with the development of techniques for collecting the data. If data is not properly collected, an investigator might not be able to answer the question under consideration with a reasonable degree of confidence. One common problem is that the target population may be different from the population actually sampled. What is the target population? The one about which conclusions are to be drawn. If we want to go and find out and study about the attendance of Korean people in an election, we must go to different parts of society, not only one part. Part means geographical. We should go to village. We should go to different cities. We should go to different points of Seoul. Or we should go ask people in different age. We should ask people with different jobs, right? Another example is, for example, advertisers would like various kind of information about the television viewing habits of potential customers. The most systematic information of this sort comes from placing monitoring devices in a small number of homes across a country. So we already studied about the target population. Now let's talk about simple random sampling. When data collection entails selecting individual or objects from a frame, the simplest method for ensuring a representative selection is to take a simple random sampling. This is one for which any particular subset of a specified size, like a sample of size 100, has the same chance of being selected. We go for random selection. Sometimes alternative sampling methods can be used to make a selection process easier. It means we want to obtain extra information or we want to increase the degree of confidence in conclusion. One such method is stratified sampling. This entails separating the population unit into non-overlapping groups and taking a sample from each one. Frequently, a convenience sampling is obtained by selecting individuals or objects without systematic randomization. As an example, a collection of bricks may be stacked in such a way that is extremely difficult for those in the center to be selected. Engineers or scientists often collect data by carrying out some sort of designed experiments. These are sampling methods and experimental design in data collections. Okay, so let's stop here and continue in the next lecture. Making predictions and determining relationships.